Hello, hello, hello.
Hello, Estes Park.
So that sounded familiar, right? We had this song last year at our keynote at LambdaConf, and this was, last year we had it without any video or something like that, but it was just a song, it was nothing else.
It was bad quality, bad generative AI quality. Yeah.
But what is this about,
Yeah,
Martin?
this is a Runway version 3 we used here, and nowadays we have Runway 4, right? Yeah.
Yep.
Good. Anyways, you want to talk about what this was, what you just saw here, yeah? So, this was a song, Thomas. I created this song and the video and everything. And do you know how? So, the lyrics have been written by ChatGPT. Okay?
Yep.
So, the music was generated by SunoAI. We created images with Midjourney, and we animated them using RunwayML. And all this stuff has something in common. It's generative AI. So, our talk is about, I'll be back, generative AI for image and video production. So, we have been already introduced, so Thomas and Martin, and let's have a look to the agenda at first. We want to have a look to text, text to image, text to audio, to video, and everything. But for this, you need to understand how diffusion models actually work under the hood, and this is all about. So, Thomas, regarding AI, there is a very important thing. What Hollywood promised to us.
Yeah.
It was this human-killing robot, the Terminator.
Yeah, and we're so disappointed because what we got was rather this one. So
Yeah.
we have people, we have robots that can paint now
Yeah.
and that are creative. And to
And-
be honest, they are not really.
Artists are arguing that AI now takes over the artist work, yeah. So AI art will make designers obsolete. AI accepting the job. So yeah, generative AI. Let's have a look on that. Thomas, the Gartner hype cycle.
Yeah, so let's see where generative AI stands in terms of the hype cycle, the hype that is there. So usually a few times a year we have a look at this hype cycle. This is the one from 2023. And you see normally technologies, they tend to start, then they reach a certain hype, then they go to the trough of disillusionment, and then they become productive. And generative AI and everything that's based on AI was at the peak of its hype in 2023. And fortunately, it's still at the peak of its hype. So what can it do? So why is it so popular?
Yeah, generative AI, what can you do with it? Yeah, you can have a text input or an image input, and you can make a video out of it. Like here in this case, we used a starting image from Midjourney and animated that with RunwayML. Yeah, text to audio, we already spoke about that. You can make music with it. And of course, this is the most well-known thing, text to text. You put in a prompt, and text output is generated. So, when we want to talk about text to image and text to video, we unfortunately have to have a deeper look into text to text, into GPT, into LLMs to understand how they work, to have a better understanding of specific features. So this is ChatGPT, you know this interface, you type something in, it comes out. And by the way, this typewriter effect, it's not just an effect, yeah? This is how LLMs, large language models, work under the hood.
Yep, because when you have something like a beginning of a sentence, or like your order has been, and then you can put that through GPT and you will get a probability distribution of what the probable or most probable next word is. So it could be something like confirmed or shipped or successfully, and so on and so on.
More precise, it's autoregressive next token prediction what we are doing here. So not a word, but a token. So Thomas.
Yeah, and this consists of three different things. So first of all, we have a tokenizer, then we do an embedding, and then we do the transformer. We will go into each of these steps right now. The tokenization might be the most boring thing about the whole process because you somehow need to represent all of what we have here as numbers. So you just assign a number to a specific word or parts of a word, and then you already have the tokenization like you have here. Welcome to the Lambda conference. You can see that Lambda is not a common English word, or not at least to the common public, then it gets split into 2 tokens, lam and da.
Right. And if you have a look to the token of 2, yeah, it has the ID 284. It appears 2 times. Both have the same token ID. Yeah. That's correct. This is how it works.
But this is not really enough, Martin, right?
Yeah, right. So now we need to get a semantic understanding somehow, yeah. And the idea is, when we have a look into the vector space, yeah, there is, for example, a distance between the token man and the distance and the token of women. And what we would expect is that the distance between uncle and aunt in the vector space should be somehow the same, or also between king and queen, so that we can somehow get a semantic understanding.
Yeah, and this is what it looks like if we have a look at one of these embeddings. So we now projected the very high-dimensional embedding that we have, the high-dimensional vector space that consists of each and every token that we have. And we can now break that down into 3D, and then you will see some interesting effects there. Not only that man and woman have the same distance as uncle and aunt or something like that, but also that they somehow related words, so words that are close by semantically, they also appear to be at roughly the same spot in this vector space. So you have, for example, here you have the first names, and they all are somehow close to each other. And the same is true for city names. So this is another part of the embeddings for one of the first transformer models that we had, namely bird. And with that, we can now play around. Yeah?
So what we did here was having a look into these embeddings, and you can see that there are sections with place names, others with city names, and so on and so on. And first names and whatever. Yeah.
This brings us to the most important part of the whole transformer thing, namely attention. Attention is basically a bit like cheating in school, right? So if you happen to have a test in school, and of course you have not learned for this test, so you don't know what to do. So what you now want to do is, you have a look to the left, you have a look to the right, you gather all the information that's around you, and then you sort this information and bring the most important parts to paper. And this is exactly what the attention mechanism does as well, metaphorically, of course.
Yeah. So speaking about attention, we want to have a look to this sentence: the prince met the king near the calm lake. So what we already told you, typically you would do some kind of tokenization. So we did that here. And this sentence could continue with something like he ... and so on. So now the question is, where does he refer to?
Yeah. So what does he mean?
He refer to, I don't know, king, or maybe prince?
It could also be the lake.
Or lake, or whatever, yeah? So this is the question. So
what we now can do is we just have a look at the context. So everything that's surrounding the word he. Of course, we only know everything up until the word he because the rest of the sentence has not been written. So we're going backwards, and then we extract. So the attention mechanism basically extracts the most important tokens or the most important words that are there in the context for the specific word he in this case. And then we can make sense of that and create the next word. So in this case, of course, very important for the word he is prince or king, and to a lesser degree maybe calm and lake or something like that. But you boil down everything that you have, all your huge context, and you can now just do a specific part or deal with a specific part of this, the condensed information of what is important for the probable next word.
Yeah, so to sum it up, we are putting it all together right now. We have our input prompt. We do the tokenization. Then we have the embedding. And within the transformer, there goes some magic on, and it will put out a list of tokens with different probabilities, which token will be the next one. Yeah, so This is
That's
how
the
it
whole
works.
thing.
We have another example for a better understanding. We have the input sentence, your order has been, and now it should do the autoregressive next token prediction. And what happens right now? It will predict a few different tokens. In this case, we used Word because it's easier to understand.
Yeah.
So confirmed with 51% confidence, shipped with 17% successfully, and whatever.
And so on and so on. And
so
now the next word. So you can now put the word that is predicted into the input again.
Yeah, right.
And with this, you can then run GPT again. So this creates the typewriter effect in the end. So this looks like your sentence is being built step by step.
Right.
And in the end, you will get something like an end of text token.
This is what happens here. So here with the highest probability, we will have the end of text token. And this is where GPT would just stop to process any more. Yeah. OK. So now you hopefully have an idea how it works, the attention mechanism somehow. And this brings us to text to image. So let's have a look to this one. Yeah, we have in prompt red apple with water droplets, neutral background, and you see different AIs doing text to image. Midjourney, Stable Diffusion, Dolly, renamed to, I don't know, OpenAI.
Yeah, image generator is something different.
Yeah, it's named different. So let's have a look when text to image started, how it looked like with this prompt I just showed you. Midjourney version 1 was released on February 2022. And this is the output of the prompt you just saw. Now, let's have a look. 2 months later. Still doesn't look that good.
Yeah.
Let's add additional 3 months. Version 3 was released. Another 4 months. It's getting better. And then another 4 months later, you can see the progress is really, really fast. And another 9 months, we have version 6 of Midjourney. And yeah, I now want an apple. So the question is, how does it work that you can generate images out of text? Yeah? And this is where CLIP comes in, Contrastive Language Image Pre-training. So what we do is the following. We have an example, 3 prompts and 3 pictures. And what we have here is a confusion matrix. So what you are doing is you compute the similarity for each text and image pair. So if you have a black office chair and you have the root to the image of the Piku panda, the red panda, then you have a very low similarity. And if the prompt a black office chair has the root to the real black office chair, then you have very high similarity. So this is how a confusion matrix looks in the end. And now you have some connection between prompts and images. And there are millions of images used to train this clip. Thomas.
Yeah, so the next thing we need to know about the diffusion model process is that it's an iterative approach. So we asked an artist to do an iterative approach himself. So this is some work that we did on was basically hired on Fiverr. So we asked one guy to recreate this beautiful image. But you can see, let's start that again. You can see that normally the artist starts with the basic shapes, right? And then he basically uses some techniques to refine some of the shapes. Then some color is added, then some shading is added. So all of this is a very iterative process, and we will need to iterate ourselves for the diffusion models as well. But what about the diffusion in diffusion models? Mark?
Yeah, the diffusion in diffusion models. So if you have a look back into the days, let's say 20 years ago or something, when you had some pictures, photographs, which have been some kind of noisy because of high ISO, then you probably you were able to see some kind of noise there, and then you could start a denoising process, but this was just adding some blur to such regions in the picture, and you probably will lose quality with it as well. And nowadays, we have a different approach when it comes to diffusion models. you need noise and noising and denoising, but let's have a look on that. So what is the idea of diffusion models on a high level? Let's imagine we have a cup of water and we just want to drop a drop of red ink into the water. Yeah? So this is our starting point. Yeah? At the time 0, the drop enters the water and then some magic happens. This one, so the drop will go into the water. This is a very, very chaotic process, and physically, physics-wise, this is not reversible. Yeah, you understand. But the good thing, we are in computer science, and here we can work with some tricks to make that process reversible to vorhersagen?
Predict?
To predict the position of the drop when it enters the water at the time of 0. Somehow. Let's have a look on that. What we are doing, we have at the timestamp 0, we have the original picture of our apple. What we are doing right now, each and every step, we add a little bit of noise. And again, and again, and again. And at the timestamp t, you just see noise, and that's it. Yeah? What do we have here? This is so-called Markov chain. So between timestamp 0, there is a relation to timestamp 1. From timestamp 1 to timestamp 2, there is a relation between both of them, but not between timestamp 0 and timestamp 2. And the idea in the diffusion model is that you do some kind of denoising, but in a completely other way than with our first example back in the days 20 years ago. And this brings us now to the diffusion process. What we want to do is we want to gather information. We need pictures with noise, knowing what was in the picture originally. So what we are doing, we have an apple here at timestamp 0. Now we generate some noise. We add this noise to the picture a little bit. And then we put it back into our input, so to say, for timestamp 1. And then we do this several times. And now you will see timestamp 2, timestamp 3, gets noisier, noisier, and noisier. At the end, you are not able to see, you can't see nothing. So, with this, you can train a neural network. Because you always have in mind, it's still a red apple. So, you can train a neural network that it can reverse process this stuff. And let's have a look on this one. So you put the prompt a red apple into clip, and clip will give us an embedding in this diffusion model, in this trained diffusion model. And what happens right now is that the diffusion model predicts a noise where it thinks this needs to be subtracted from our generated noise so that we then have our output image, our apple. But if we start from the last time step, you probably will have still some kind of noise or a blurry, very, very, very blurry image.
It will not work perfectly.
So, but what you're doing is, as it is an iterative process, you just subtract that. And you do it again and again and again, time step 6, and again and again and again, till the final image. And then you hopefully have your output image, which is an apple. But there is one important thing, because it's not really 100% correct in these slides. It's very, very unlikely that you will get an image out of your diffusion model which looks exactly the same like it was used for the training data. This is important to know. Yeah? Okay, Thomas.
All right, so now with all the theory done, let's have a look at an example. So we now have a demo for that, of course, and we can do something like...
do we want to ask the audience, or do we want to...
First of all, we'll create a beautiful landscape, so a fantasy landscape with mountains and a river, because we are in Estes Park. That probably fits pretty well.
Okay, then we do it like this.
And we are now doing the demo. So you can see...
Time left, 263 years, okay.
Yeah, and it's getting
3 hours, okay.
Yep, and as you can see, in the current step, we have the predicted noise, and if we just subtract it completely from the initial noise, then we'll get the thing on the right image. And you can see that the iterative process is now going on. It will predict, the noise will somehow be better than it used to be in the first step, and it will resemble the final image more and more. And if you subtract that, it will also get better over time. And in the end, we will end up with something like that. So this has been 10 steps now with a Stable Diffusion XL model, which is not the best model that is around these days, but just to show you what the process looks like, what the noise looks like. And you would also probably need like 25 steps or to have a good picture or something like that, but we wanted to speed things up a little bit.
Yeah.
All right.
So I would say we just continue with our talk, and if we got some time, we can try it again. Yeah. Okay, so now we want to talk about guidance. What is that, Thomas?
Yeah, so guidance basically means, so you have this beautiful picture from a medieval church and you want to restore it, yeah? So if you just do it the naive way and say, okay, I don't have any clue, I don't have any context or anything like that, you might end up with something like that. So this is actually what some folks thought it would look like, or what the original looked like. So if you have some guidance, if you just say, okay, this is a picture of Jesus Christ, and it's also, he's wearing a thorn crown, and so on, you might end up with something like that, which is closer to the original, but to be honest, both of the pictures have something...
Have their advantages,
Have their advantages. For example, the picture on the left, the color dynamics, I like them better than in the right one. So
and on the right one, there are some scratches and missing color parts and stuff, yeah?
So you can have just the denoising process without the prompt and with the prompt, and then just interpolate between them a little bit, and then you will get the advantages of both of them. And this is what we are calling guidance here.
Right.
All right.
Okay, so now it's time to talk about the autoencoder, Thomas.
Yeah. So up until now, everything was on a pixel level, right? So we did everything basically for each and every pixel. We predicted the noise and so on and so on. So this is a good process that you can have, and some of the image generators out there do exactly that. But you could also have a look at the so-called autoencoder and try to compress what we are trying to compress our iterative process. So what you can do here is you have a neural network that consists of two parts, namely an encoder and a decoder. So what you do now is you put the image of the apple into our encoder. This will compress the image to its most important parts. So you train it to compress it to, for example, if you have an apple, you will have something like, this is a round object. It also has a stem in there, and it is also red. Yeah. So things like that will be trained into this latent space. And with that, we can just use the latent space, put it in the decoder again, and then we get the same image out again. Yeah. And what you have then is you can now just not only train on the pixels that you have, but on this compressed version of the pixels.
Right. So instead of working on the pixels, you are working on the visual features of an object, which needs not so much time, computing power, or whatever, or inference power.
It's just lower dimensional.
Right. Yeah, okay, and so instead of working on the pixel basis, you would now have something like that, You still have a red apple as a prompt. It goes into clip. Clip puts out some embedding. And then instead of working on the pixels, you are working on those features, on this abstract level of these visual features.
Yeah.
Yeah.
And since we are working in the latent space right now, the compressed version, this is called a latent diffusion process. And with that, we now created the images. So what next?
Right, so now you learned how a diffusion model works, hopefully. This brings us now to text to audio, text to video, because everything relies on that stuff. So let's have a look to text to audio. When it comes to audio processing, you probably have seen something like that. Yeah, so you can see the amplitude of a left and a right channel within audio software. And the question is, only based on the amplitude, are you able to understand which song this is? Probably not, because you also need information about the frequencies which are somehow played. What can you use to show a frequency? F50, yeah, awesome. A spectrogram, I would call it like this. And this is actually what we have here. So now we have the amplitude and we have the different frequencies. Yeah? So, don't mute my own made music. Yeah. Okay. Yeah, it's my copyright. Yeah. So, we have a spectrogram here right now, a spectrograph right here, and spectrogram. We have now information about frequencies, about the amplitude as well for the different frequencies. And now guess what you can do with this stuff?
Oh, this looks like an image.
This looks like an image, right? Why not training a diffusion model with spectrogram images so that it can predict how will a song somehow continue? You know what I mean? Yeah? So, and this is actually what we learned in our research. We don't have official information from SunoAI about that. But this is something we stumbled upon.
Yeah, the first thing that was created this way was Refusion. And Refusion, basically, the idea sounded stupid at first, but it really worked. And then people just worked with that and made it better and better and better. And nowadays we have all these beautiful text-to-audio models, which is pretty cool.
Yeah, SunoAI, AI, what else? Yeah, these are the most common, I would say.
Yeah, there are also open source models available. Yeah.
Right.
All right.
Okay, and now text to video.
Yeah.
We're almost through because the hard part was diffusion model stuff. Thomas, let's discuss a typical real video.
Yeah, so you can see here we have a video, and such a video normally consists of multiple frames, right? So you have a lot of those frames, typically like 30 or more per second, and you could then basically just do what we did with our text-to-image process. So just use the diffusion models a few times and then basically just create images all over and over and over, and then you have a video.
You could do that, but there is one big problem. For all of you already using Midjourney or other text-to-image AIs, you probably know if you type a prompt, you don't get consecutive frames of an image or something like that. They always look very, very different. So now imagine you create a picture of an apple. Now you have 4 of them, all different, and then you put that into a video. How does that look like? Yeah, not like a video. Yeah. So you don't have the temporal consistency and everything. Yeah. And this brings us to one of the first examples we created with Runway. I don't know, 1 or 2 back in the days. I think this was in Edinburgh or something like that.
I think that's Buddha.
Or whatever.
Yeah.
So, but now let's have a look to a very specific part here. Yeah. So this guy has superpower. Yeah, he can just melt into, into the ground. Yeah. So this is a real problem: temporal coherence and motion dynamics. Yeah. And also, so text-to-video and image-to-video AIs, they don't really have, they don't know about physics. Yeah? But there is something we can use. We learned in our talk today.
Yeah, there was this transformer process, right? And
Yeah,
this
attention.
Yeah, you could just predict the next frame or the next token based on the previous tokens. So we could just make use of that for our video process as well. And then we have our diffusion transformer actually, which basically takes the diffusion process but creates a video from that, a consecutive number of frames, each of them being an image.
Right, but there's still a challenge.
Yeah.
It's this one. It's the sheer scale of videos. So let's imagine we have 10 seconds of full HD video with 24 frames per second. These are
a lot of
values. A lot of values. It's really crazy. So we need another kind of abstraction. Yeah. So the solution should be somehow divide and conquer. And what we can do right now is we just put it, divide it in patches in the first step.
You can just have a look at parts of the image, and this will break down the process a little bit, but we will have to have a look at the edges of these things, because you cannot just do one patch at the same time, but you have to do like the surrounding patches as well, so that they are consistent within something like that. So there has to be some overlap, but this is doable.
Yeah.
And
so, but there is another possibility. We can make it a little bit more easier we use another kind of abstraction level. What was that? We already learned that today with the autoencoder. Why not working with these visual features here, and also the latent space with these compressed representations of images?
Yeah, and with that we now have the final process. So we can now take our images that we have, put that into our latent space, then splice them up into some patches. We will then use these our diffusion transformer that we have, give some guidance with the clip prompts. Then we will get a diffused version of all of our frames. We can then put them together, all of our patches, then we can put them together. We will get the latent space representation of our frames. We can then subtract that. So this is the noise prediction. We can subtract that. We can do this iteratively over and over again until we end up with something that should be a bunch of frames. We can decode them using the latent space, decoder, and with that we have our frames, which we can just put together into a beautiful video.
Yeah. Okay, so now we have a pre-baked open Sora demo because this laptop is too weak for the inference right now here. Yeah. So
the thing is, Open Sora is basically the first re-implementation of text-to-video thing model that we had, and we can use that to really do that. And this is the offline demo that we have right now. So as you can see, it always predicts the complete video, the noise for the complete video. And then we can subtract it again, and we will always, in each and every step of our process, like 10 steps that we have, we can basically predict the noise of the complete video of every frame. And at the end, we will end up with something that resembles somehow a drone flight over a lake there near Munich, actually. So this is what we created with Open Sora, and of course, this does not look very good because we are using 10 steps. We are using a model which is not the best one, but just the one that we could get our hands on, and at the same time, which was easy enough to extract something like the noise or something like that, so we could get insights into the whole model. Nowadays, you would use something like RAN 2.1, which is the best open source model that is out there for creating videos these days. So, yeah. Martin, what did we do with that?
Yeah, so we went to the Arches National Park 2 days ago, and we thought it could be really nice to have a nice picture of the landscape there. So like here. And now we put that into one, and let's have a look what happens. So what was the prompt, Thomas?
The wind blowing the cup away or something like that. Yeah. You can just go backwards and.
It's not looping anymore.
No, it's not looping anymore. Yeah, that's right.
Yeah. Yeah. So this is what you actually can do. And if you are more interested in the photo series of cups in front of beautiful landmarks. Just visit our photo love story, Arches National Park, 2 cups, 1 park, by photographing the QR code. So this is our kind of humor, and hopefully you will share it. Okay, Thomas, just let the people photograph the QR code. The next slide would be about applications of a video diffusion transformer. We can do that just by telling them.
So there are multiple things that you can do now with these things. So first of all, of course, you can do something like image to video. So you can not start with a text prompt, but an image prompt. So for example, you have this beautiful video, this beautiful frame here, and then you can just extend that into a video.
Yeah. Let's have a look to the next one, video extension. So you start with a specific video part, and after that you just let extend the AI the video. So here we have 2 different, they start with the same frames, but now you can see they go into different directions. Yeah, nice. San Francisco with flying cable cars. Really nice. Next one, video interpolation. This is an interesting thing, Thomas.
Yeah.
Maybe you want to talk about that?
You start with a video and you end with a video, and then you try to interpolate between those 2 videos. So every time the animal looks away now, it looks less like a gecko and more like a
the bird.
Yeah.
Yeah.
And this is kind of interesting because you don't see the difference that much. At the end, you will find, what the fuck just happened?
Yeah. So last but not least, video editing. This is going to be interesting. So you have your original footage of a red car on the street. And now you can change the environment. For example, now it's driving underwater. Yeah. Or here, like in a medieval setting with a horse. Or here in a Minecraft 8-bit style. Yeah. So this is going to be interesting probably also for Hollywood. Okay, now understanding gaps in AI. So there are still problems. Like you can see here, it's about physics. We already had that. There is just an apple popping up, but nobody knows why and when, whatever.
And it's pretty magnetic.
Yeah, it's pretty. Yeah. So this is probably not the kind of special effects you want, but let's have a look to this one. This is from the Sora demo paper. Maybe some of you already know this. Yes, there's just a chair popping up. Yeah.
Yeah. And
nobody
it's flying
knows.
Around.
It's flying around and everything. So this is still a big problem and needs to be challenged. So when it comes to physics, let's talk about sports. So there was a guy trying to generate Tour.AI, and this is how AI imagines the Tour de France. Let's have a look on that. So we don't know why it looks like this. So we have a few ideas. So on TV, when Tour de France is shown, they probably repeat very often such accidents, because it's interesting. Oh my God, an accident. So maybe this is the reason why it looks so scary. Okay, so. Although if this is very fun, we need to become a little bit more serious right now. It's about ethics, but we don't have so much time to talk about that. But at least we want to mention it. Some AIs have probably been trained without the owner's consent.
Yeah, who doesn't know Shooterstook?
Shooterstook. You know it? Shooterstook? So it's probably being trained without the owner's consent. And
This doesn't end here.
Yeah.
So even if you, so people tend to have a specific kind of amnesia when it comes to training data and knowing where it came from.
Yeah.
So this is the CTO of OpenAI.
What data was used to train Sora?
We used publicly available data and licensed data.
So videos on YouTube?
I'm actually not sure about that.
Okay. Videos from Facebook, Instagram?
You know, if they were publicly available, publicly available to use, there might be the data, but I'm not sure. I'm not confident about it.
The interview is hilarious.
the interview is hilarious, yeah, that's clear. So, yeah, there are legal challenges going on, and it's not only for Sora, it's also for SunoAI and stuff like that. So the German GEMA, for example, I think they also had a lawsuit against SunoAI, right?
Yeah, absolutely, and there is some truth to that. So they were really trained on the audio that is probably not under copyright and things like that.
So what do we have here? Zuckerberg approved Meta's use of pirated books to train AI models, authors claim.
So basically, this is probably why Llama 4 is not that good, because they had to cut back on the training with the pirated books. Maybe that has to do with that a little bit. Yeah.
The funny thing is, if companies like OpenAI steal data to train their neural networks, it's interesting how they react if someone else is stealing data by prompting their product to train their neural network.
Yeah, it's always, it looks like a little bit like this one.
Yeah, think about DeepSeek, yeah, so here, this awesome cartoon. Because DeepSeek, how did it work? So they they prompted against ChatGPT, they gathered all the output data and trained their neural network with it. And this is, this is the way it works. Yeah, out of scope topics in our talk. So, when we talk about labor rights and labeling and after job displacement, is a thing.
Yeah, these things are trained with labor that is probably not, there's not much payment for that, and it's also done in a ethically not okay version of it. And
Let's talk about training data oligopoly, because OpenAI has somehow a data oligopoly right now. Why? Because they trained their deep neural network, their ChatGPT and everything, and nowadays there is so much AI stuff generated and published in the internet that it can get somehow
it's poisoning.
It's poisoned. The internet gets poisoned by AI-generated data. And the problem is right now, if you just want to start a new LLM right now, you probably will train it with poisoned data, which is maybe not that good. Yeah. Okay. Disinformation, of course, such AI can be used for disinformation. That's totally clear. Yeah, can generate fake news in a few seconds, or create pictures of politicians doing things they would not do, at least not in the public.
Yeah, and there's of course a right of personality, which is also related to that. And for that,
speaking about right of personality,
let's have a look at this video. Yeah. So, for those of you who have a closer look to the video, this might not be the real Will Smith. So have a close look.
Probably.
To it. Yeah.
But text to video, it has such a fast progress. Look at this one, February 2024. It looks really amazingly good, right? So actually, to be honest, this video is real because Will Smith came in contact maybe with the original spaghetti video, and he made some fun out of it and posted. I think he posted that on Instagram, on his channel. But anyways, it's really interesting to see how quick, how fast the stuff of generative AI progresses. So I would say text to image is already nearly perfect, I would say. This is not true for text to video, not yet. But with RunwayML 4 and with Sora, it goes into the right direction. And this is now the end of our talk, and we have
some time for questions.
That's amazing.
What's happening here?
Thank you so much. Thank you.
So, have you heard of any like recent like advances in trying to like alter kind of like the architecture of like text to video models that allow for baking in structure? Like with text models, we have ways in which we can alter the generation to get structured outputs, like enforcing JSON like on the token level. Is that something that we can maybe also apply to video to enforce things like physics constraints like on the generation instead of just looking at the output and then trying to fix it afterwards? I know that's a big question, but
the real answer is we don't know about papers for concerning that. So the latest one that has been released is one, and I'm not sure. I'm not sure if it has these concepts baked in, but if you still have a look at the models that are around these days, they probably have just been trained on more data and some advances in the architecture, but not on a physics level.
Yeah.
But I could imagine baking that into some kind of extra embedding that you would do. But I have not heard about real-world
But then you would need
models.
the real-world data of what you are filming and the real-world data of what is moving around and stuff like that, yeah, to put in a physics layer somehow. Yeah.
Yeah, so you mentioned this physics layer and this idea, like, how do you embed physics or how do you embed a world model into this? Is it, do you use control net? Do you use, how do you model it out in spheres and orbs, and then, or how do you ensure that the bikers are facing the right way, or that there's some coherence there?
Yeah, that's a good question. So I would think so. Again, the literature on that, we haven't read about anything that would embed physics into the process itself. But then again, you could have a look at the transformer architecture and just find some invariants that you need in there to represent some physics that they face the right way. And you could also guide the process with a better latent space representation, where you can really have not only the features of the image that you have, but also some physical properties. And you could also have that in your latent space representation and then guide the transformer on that.
Hey, I guess kind of related to the physics and the generation, is text to 3D models, like CAD models, is that a thing that's kind of picking up? I would assume, but I haven't heard.
Yeah, there's a lot of movement going on in the field of text to 3D. So up until last year, it was really hard to do that. But nowadays there have been a lot of models popping up that can really create beautiful 3D models. It's a Chinese model.
Don't ask me.
Yeah, I already forgot the name again because there are so many models coming up. But there's also Meshi in the commercial space, or CSM, which can create 3D models. And there's also a new thing, text to Lego. So I haven't tried that out, but it can create Lego models.
So, thank you very much for your talk. It was really inspiring. And
Thank you.
Thank you.